We're at a point now where we've learned how to apply the law of conservation of momentum to collisions and explosions in one dimension, where all the motion is along a straight line. And then we've learned how to work with vectors in two dimensions, how to add them, how to subtract them, different strategies for doing that. So this lesson is about combining those two skills and those two ideas together. We're going to apply the law of conservation of momentum to collisions and explosions, but in 2D situations where not all the object motion is along one straight line. So the key thing to remember here is when dealing with collisions in two dimensions, it's important to remember that momentum is a vector with magnitude and direction. So when finding the total momentum, as the law of conservation of momentum requires, we're no longer just adding positive and negative numbers, as we did with 1D momentum problems. Instead of just being plus or minus, momentum will now have a direction like 30 degrees north of east, which can't be simply reduced to a plus or a minus. So instead, what we're going to have to do is proper vector addition, meaning drawing the two vectors out, putting them head to tail so they're being added, and doing some trigonometry to find the solution. So I've picked one problem here that I think is going to illustrate a bunch of different things we need to consider on this topic. And we're going to go through it, making a few notes along the way and trying a few different strategies. So here's the problem. In a game of pool, a 0.17 kilogram cue ball traveling 1.3 meters per second north strikes a stationary 0.16 kilogram 8 ball. After the collision, the 8 ball has a velocity of 0.6 meters per second at a direction of 31 degrees east of north. What is the velocity of the cue ball? So if this were a 1D momentum problem, I would advise you to start by splitting your page into two and drawing a diagram on each side. And so that's exactly what we're going to do. We're going to start by splitting my page into two. Initial over here and final over here. This side is for things that are happening before the collision. This side is for things happening after the collision. And I'm going to draw a diagram. And what I'm going to do to make things super clear, I'm going to use different colors. I'm going to use green for initial. And I'm going to use red for final. So, initially, we've got an 8 ball that's stationary and a cue ball moving towards it. So, there's my 8 ball. And then I'm going to have a cue ball traveling north, moving towards it. So my cue ball is going to be coming from here, heading up. Now, what might strike you off the bat as a little odd about this problem is the direction the 8 ball goes in. If the cue ball was traveling north and it hit a stationary 8 ball, wouldn't the 8 ball then just travel north? But that's not what we see happening. The 8 ball is traveling east of north. The 8 ball heads off in this direction. How can that happen? You'd think if we wanted the 8 ball to head off in this direction, we need the cue ball to come from the opposite direction. But somehow, that's not what we have here. And what you may be starting to realize is that, well, if the cue ball actually doesn't hit the 8 ball head on, if it kind of hits it a little bit off center, then they might kind of both head off, bounce off to the side. So indeed, that's what's going to be happening in this situation. My cue ball is going to be over here, heading towards the 8 ball. Okay, so let's throw some masses in here. And my velocity. So this, here's one little note I'll add. This is what's called an oblique collision. When two objects collide and they're a little bit off center, they're not hitting head on. The center of this is not in line with the center of this. And that's this is a common type of problem that comes up in 2D collisions. So let's write a note about that. So an oblique collision is when the objects strike each other off-center, not head-on. And that's what we have here. Okay, so what's happening on the final side, after the collision? Well, we have our 8-ball. There it is. And it's moving off with a velocity like this. And we have our cue ball. Now I guess if the cue ball hits this off center and kicks the 8-ball that way, the cue ball is probably going to head off this way. But I don't know exactly what direction it's going. I don't know the exact angle. So I'm just going to draw my cue ball sort of over here. With some velocity. But I don't know what it is. I suspect it's going to be heading kind of in this direction, but we should be able to solve that and find out for sure. Again, this guy's 0.17 kilograms, and this guy's 0.16 kilograms. Okay, so the next thing I'm going to do, again, just like if this was a 1D conservation of momentum problem, is I'm going to use the law of conservation of momentum. Total momentum initial equals total momentum final. Remember, we can only use this if we're talking about an isolated system or one that can be approximated as being isolated. In the case of pool, these things are rolling, so there's not a lot of friction to worry about. Both balls have normal force and gravity force, but those basically cancel each other out. So there's not many external forces that won't cancel each other out. That makes this pretty isolated. Now, let's, you know what, I'll even keep going as if this was a 1D problem, and I'll plug things into this equation. So on my initial side, I've got two initial momentums that have to be added together. The 8-ball's momentum, which is 0, because it has no velocity, and the cue ball's momentum, which is going to be mass times velocity. Momentum is mass times velocity. So here, I have the cue ball's mass, 0.17, times its velocity, 1.3 north. Okay. On the other side, I have to, again, add the momentums. So add the masses times the velocities. The 8 ball, there's its mass, there's its velocity. 0.16. The mass, the velocity is 0.631 degrees east of north. And I also have another momentum, the momentum of the cue ball. So I'm going to add those two together, right? I'm adding all the final momentums. So this will be 0.17 times the velocity of the cue ball. That's the thing I don't know. We're just calling that v. So here's my formula. The sum of all the initial momentums is equal to the sum of all the final momentums. At this point, I'll point out that this is a common place where students make a mistake. They often look at their diagram and they know they have to add some vectors together, so they just start taking this vector here and this vector here, and they throw those into an equation. Remember, these are velocities. But this equation specifically references momentum. So be careful you don't just add the velocities together. You need to multiply them by their masses to turn them into momentums. Velocity is not conserved. Momentum is. So that's a little note we'll write here. Add the momentums, not the velocities. All right. So next up, we are getting to the point where we need to start actually doing some math here. We need to start adding some stuff or isolating v in this equation. And remember, here's where the 2D part becomes important. If this was a 1D problem, we would just have positive and negative numbers that we could plug into our calculator. But because it's a 2D problem, we need to do vector addition. We need to draw these puppies out and put them head to tail. Now, there's a couple approaches we could do. Some of you might like to say, okay, I'm looking for v, so let's rearrange this equation and isolate v. I'll move this vector to the other side by subtracting it, then I'll divide both sides by 0.17, and then that'll give me, I'll have an equation that says v equals, and then I just do my, my vector addition, my vector algebra on this side. That would work fine. Another way we can do it is by just kind of taking the equation the way it is, and there are some advantages to each method, but this is the one I'm going to do right now. So what this equation basically says is there are two vectors, and if I add them together, that means if I put them head to tail, they will give me a resultant of this. I can kind of draw that out. So one of my vectors is 0.16 times 0.6. So maybe I'll actually calculate that out right off the bat. 0.16 times 0.6 is 0.096. And on this side, 0.7 times 1, or 0.17 times 1.3, 0.221 north. I should get in the habit of putting my directions in square brackets. Okay, so this vector plus this vector, so those two are head to tail, they're being added, should give me a resultant of this. So I'm going to draw these out. Let's go like this. there's this vector. Now I'm adding to it this vector here, 0.17v. We could even just write this as momentum final, but we don't have to. Let's write it as 0.17v. Problem is I have no idea which direction this is going in at all. It could be going like this, 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 it could be really long and going down here like this. The point is, because these are being added, they will be head to tail. So this vector is going to start here and go somewhere. But I know that my resultant, remember the resultant goes from the very start of the first vector to the very finish of the last vector, is straight north. So my resultant, which starts down here at the start of the first vector, is going to be going straight north, and it has a magnitude of 0.221. So now I can see if this is my first vector and this is my resultant, then the thing I have to add to this to get that is going to be this guy here. That's my 0.17 b. So I've taken my equation and I've turned it into a vector addition diagram. The 0.096 plus the 0.17 equals the 0.221. 0.096 plus the 0.17, so those are being added, they're head to tail, equals 0.221. So 0.221 is my resultant. And again, remember the way I've color-coded things here, green is initial before the collision, red is final momentum after the collision. So before the collision, I just have momentum going north. After the collision, I've got one momentum going this way and one momentum going that way, which is kind of what we suspected in our diagram. Before the collision, I've got just momentum going north. After the collision, I've got one going this way, and as we suspected, this guy is going to have momentum going that way. So those are these two vectors down here. At this point, we now basically just have to solve this triangle. And there are a couple ways we can do this. One, this is not a right angle triangle. So if it was, we could use Pythagoras, we could use SOHCAHTOA, and that would be great. Because it's not a right angle triangle, we have our choice of either using sine law and cosine law, which work on all triangles, or of using components. And I think what I'm going to do for this lesson is I will do it both ways and demonstrate both of them for you. So if we use sine law and cosine law, let's say we use cosine law to find the length of this guy. This is the guy we're trying to solve for, right? We're trying to solve for v. So when I'm using cosine law to find a side, it makes sense to make the side I'm looking for side C, and then the opposite angle will be angle big C. So if I apply sine and cosine law, I get C squared equals A squared plus B squared minus 2AB cos C. I won't go through all the steps here, but I'll tell you what you should get by going through this. So we know C is the thing we're looking for. A and B are going to be this length and this length. And angle C is this guy down here. It's my 31 degrees. So this gives me C is 0.14726. So that means that V, so C is 0.17V. So then that means V is that divided by 0.17. 0.86624. So that tells me the magnitude of v, but v is a vector. It needs a direction too, so I need to find the direction this arrow is heading. We always define a vector's direction from its tail, so that means I need to find this angle down here. Let's call that angle A, which means this side is going to be side A, opposite angle A, and I'll use sine law to solve for that. So sine of A over A equals sine of C over C. Let's solve for A and see what this gives us. So that gives me 50.6 degrees. But you should be a little skeptical of this, because looking at this angle here, I didn't draw my triangle perfectly to scale, but I did an okay job. This looks like an obtuse angle. This looks like more than 90 degrees. It doesn't look like 50.6. And here's where we have to remember something really important about the sine law. You can use the sine law to solve for any angle in any triangle. And those angles might be obtuse. They might be more than 90 degrees. But when you take inverse sine to solve for your angle, it will always give you, your calculator will always give you a number less than 90. So how do we reconcile that? I can solve for an angle that's greater than 90, but when I go to find it on my calculator, it always tells me a number less than 90. One thing your calculator is just going to assume you remember is that there are two possible answers when you take the inverse sine of a number. One is the one your calculator gives you, which is called the reference angle, and one is 180 degrees minus the reference angle, minus the one your calculator gives you. So in this case, the other option is 129.4 degrees. That is a really important thing to remember. Important enough that I'm going to write it down for us here. This is called the ambiguous case of the sine law. So, when you use sine law to find an angle, there are two possible solutions. The one your calculator gives you is called the reference angle. That's the one we got here. The other possibility is 180 degrees minus that. This one over here. You need to decide which is correct. So that's where drawing a triangle that's relatively to scale comes in handy. I can look at this and say, you know what, that's definitely got to be bigger than 90 degrees based on what I know about this triangle. So of these two options, I'm going to pick this one. So now, the issue is that doesn't actually, it's not the final thing I need to describe the direction of this vector. To describe the direction of a vector, we want to go to its tail, like we did, and we want an angle that compares it to one of our compass directions, so to north or to west in this case. This angle does not compare my vector to north or west. It compares my vector to this other vector here. So I'm going to have to do a little bit of geometry here. But if I take this triangle and I kind of insert a line here, I have a right triangle down in this corner, which means this is 90 degrees, so these two angles need to add to 90. So if this is 31, this guy should have to be 59. So this angle here is 59 degrees. And so if this is 59 and this is 129.4, I can subtract those two to get out what this last guy here is. And that tells me that this guy here, 70.4 degrees. So, my final answer for B, the velocity of the cue ball after the collision, is going to be 0.866 meters per second. At a direction of 70.4 degrees north of west. Now, as promised, I want to solve this problem a second way. So, we started the problem, initial and final, diagram of before, diagram of afterwards. We applied the law of conservation of momentum. But instead of then putting all my vectors in, including their full direction, and changing it into a vector addition diagram, I could have, at this point, gone directly to components. And I'll show you what that looks like. So, if I use x and y components, what's nice about the law of conservation of momentum and other laws is that I can apply it to just the x components, and it will still be true. And I can apply it to just the y components, and it will still be true. I don't have to apply this thing in both directions at once. I can use it in each dimension at a time. And I'll show you what that looks like down here. So this is the components method. So, if I look in just the x direction first, I can say the total momentum initial in the x direction has to equal the total momentum final in the x direction. So let's look at what's happening in the x direction. Well, initially, in the x direction, I've got nothing. This guy has no momentum at all, and this guy's momentum is all y. So total momentum initial in the x direction is 0. How about in the y direction? Well, or how about total momentum final, I should say. How about total momentum final? Well, over here, this guy probably has some momentum in the x direction, right? We think he's going that way a bit. And this guy has some momentum in the x direction. In fact, I can calculate what this guy's momentum in the x direction is by drawing out its components here. A little bit of quick trigonometry shows me that the components of the velocity here would be 0.6 times sine of 31, 0.30902, and 0.6 times cosine of 31, 0.51430. So these are my y and x components of this velocity. So to turn those into momentums, I just have to take them and multiply them by the mass. So looking at my x components, on the final side of things, I have whatever's this guy's x component is multiplied by its mass. So mass is 0.17 times the x component of velocity. We'll call that Vx. And this guy's mass, 0.16 times the x component of its velocity, which is going to be 0.30902. And that is in the positive x direction. So that's positive 0.30902. Okay. So now, by just applying conservation of momentum in the x direction, I can solve for Vx. Let's go ahead and do that. And I should get negative 0.29084. Okay, that was actually pretty quick. I went from here to finding the x component of my velocity in like kind of 3 lines of algebra. Compared to over here, I had a couple of lines of subbing stuff in, and then I had a triangle, and then I did cosine law, and then I did sine law, and then I had to remember the special case of the sine law. And that gave me this angle, but I had to find another angle. So this method's looking pretty good, but we're not done it yet, because we've only done the x direction. Conservation of momentum has to be applied in the y direction too. Total momentum initial in the y direction equals total momentum final in the y direction. Okay. Well, initially, in the y direction, this guy has no momentum, and this guy has a bunch of y momentum, mass times its y velocity. So that'll be positive momentum. So it's the mass times its velocity. I've done those backwards, but that's okay. Mass times velocity, and that's positive. Okay, so I have initially some positive momentum. That means finally I'll end up with the same positive momentum. This guy's y component of his momentum is going to be this y component of velocity times its mass. And then this guy is going to have a y component of its momentum too, which will again be its mass times the y component of its velocity. Again, I can solve this for Vy to find out that the y component of the velocity is 0.81595. And I noticed when I was doing this that I made a little error up here. This 0.13 should be 1.3. So let's correct that now. Okay, so by applying conservation of momentum just in the x direction to the x components, I found the x component of my velocity. And by applying conservation of momentum just in the y direction to the y components, I found the y component of my velocity. So to get the total velocity, I just need to combine these two together, and a quick right-angled triangle will help me do that. So my y component is 0.81595. And my x component is negative 0.29084. So combining those together gives me my total velocity. I'll leave it up to you guys to do that, but a little bit of Pythagoras to get the magnitude, a little bit of sine, cosine, tangent to get the direction, and we will get the exact same number that we got here through using sine law. So there you have it. 2D collisions. Quick recap. We're going to start just like we did with regular 1D collisions. Initial and final, quick diagram. Draw velocities and masses. Then we're going to apply the law of conservation of momentum, but we have two options. I can split everything into components and apply that law in the x direction to find one thing, in the y direction to find something else, and then combine those to find my answer. Or, rather than splitting into the x and y directions, I can look at both dimensions at the same time. By just keeping my full directions, complete with angles and compass words, I can draw them out head to tail with their full directions, not just looking at x or y components. And then I can solve that triangle using sine law and cosine law. Remember, there's this weird thing that sometimes happens with the sine law, where your calculator gives you a number less than 90, but the actual answer is more than 90, and you need to know how to work with that. But either way you do it, sine law, cosine law, or components, you're going to get the same answer in the end. You'll find some questions are a little bit easier or work better with one method. Others will work better with the other. You might also find you have a preference for one over the other. And you're going to probably balance those two things out when you decide how to do problems in the future.